From École Polytechnique, right? Who's going to talk about random differentiable dynamics on the circle. So welcome, Graccyela.
Thank you. Thank you for the organizer, for the invitation, for this opportunity. Well, I would like to speak today about the random differential dynamics on the circle. I will start presenting some principal difference between the random dynamics and the classical dynamics. What I mean with this, let's put first what is the maps what we are working on is diffeomorphism of class C2. Here we know that all this set is already very well known for all of us, I think so. Well, you have isometries, or you have some parabolic maps, or some hyperbolic maps. And in the, what is this? In the classic dynamics, what you pick a map, and you want to understand how is the behavior of the orbit according to these maps. It doesn't work. Okay. How is the asymptotic behavior, or how is this orbit? It is finite, or it is dense, or what happened with this orbit, or if it accumulates in some place. Also, you want to understand if there is a unique minimal set, or if there is a unique invariant measure. I mean, with the variant, this blue equality. Or another question that you can ask here is how are the set of the accumulation points of this empirical measure. And for sure, all of you know that this set is is a subset of the invariant measure under F. Here, what we work on is we work in a random dynamical. I mean that each time I will choose in this instead map, always applying every time the same map. I will choose every time a different, well, not different, but every time a random map according to a distribution that I will fix in the beginning. For example, you can pick two maps, and let's play honestly. And we are going to choose every map with the same probability. And we can ask the same or the analogous question that we have in the classical dynamical system. How is the behavior of this random orbit? I mean random because these maps are random maps, okay? This now is the first difference between this random dynamics and the classical dynamics, because for every choice of this sequence, you can have maybe finite, you can have maybe dense set, okay? But here, how we have a probability, what we want to understand is this behavior for almost every choice, okay? Or maybe how this orbit distributes in the circle. Other question that you can have is, for example, how they are the accumulation points, the measure that are limits for some subsequence of these empirical measures. And, well, how in the classical case that we know that all the maps are the same, Fn is everywhere always the same. We know that in that classical case, all the accumulation points are invariant for the map. Here, what we have is that is also a classical result. Instead, it's a classical result of 62. It's a result of Forsenberg that say that all of these accumulation points are a stationary measure. A stationary measure I will define at some moment, but already we know from the mini course of Palis and Aaron that is in some sense invariant on average, okay? Well, for example, let's put two examples of these two maps. This first is the hyperbolic, the north and south pole, one attracting, another repelling, and the irrational rotation. The second example, F is a parabolic point, and the second is an isometry. Here, in the second example, what I assume is that they don't have a common fixed point, okay? And, well, first thing that you can note here, in both examples, there is not a common invariant probability measure for F and G simultaneously. Something that you can see here is, for example, in the first one, you have a maps that is hyperbolic, but the second is some irrational rotation. Okay, and the second example, you have that both maps are not hyperbolic in no sense. But instead, we have two nice properties. The first one, that there is not an invariant measure. Okay, how I say before, that it means that there is not a measure, a probability measure that is invariant for every map, in this case for F and G, okay? And the second condition is proximality. In this case, it's global proximality because it holds for every 2 points in the circle. You can find a subsequent in the semigroup generated by G and F, in this case G and F, in the other cases this. Okay, and you can find this sequence that these points are close how much you want. Okay, this property we call proximality. And with Catherine, we work that these two examples, we have a property that in fact present a very different behavior from the classical orbit or for the deterministic orbit when you have always the same maps. This property is called contraction average, and it says that there exists a metric equivalent to the usual metric D. The small d is the usual, and this D is a metric that you can construct for these maps that satisfies this inequality. It means that if you take the average of the images of the X and Y according F and according G, and you average this distance, what you get is a contraction. Lambda here is a constant in 0, 1, okay? And this holds for every 2 points in the circle. Okay, why this is a big difference? Because if you are in the classical dynamical system, you have a unique map. And then this map is a diffeomorphism. You cannot have some global contraction in that case. Then here, what you see is that in average, the behavior in average is something very different that in the deterministic case. Also, that you can see, or you can note, or maybe it's a surprise for you, because here you have two maps that they are not hyperbolic. They don't have a region that you can see, this is a contraction. You cannot see something like this, or maybe here in these two maps, because here, for example, you have a region that you have expansion for F, but for G is like a region that is like asymmetry, and how you can see that, then this is a case that you can get for these two properties, okay? Maybe to verify the second property, the first property is easier, because in the first case, the unique invariant measure for F are Dirac's, and in the for G are Lebesgue. They are different for sure for any atomic. For the second case, the first condition, also the unique invariant measure for F is the Dirac in the parabolic fixed point. And for the second, for G are Dirac's average, the two Diracs or the Diracs in the fixed point. The second condition also is easier to prove because it speaks about proximality. So about existence of a sequence. So its property doesn't depend on the probability of that you put for every map. We wanted to play honestly. I will put the same way for every map, but you can choose every map with some probability. Maybe F if your favorite. I don't know. But okay, in the first case, how you prove this? How you can see this second property is that you have 2 points. Okay. And then you rotate a lot of time until no one of these points are the repelling point for F, and then you apply forever F to get contraction until they converge both of them to the attracting point. For the second case, it's easier because every 2 points you apply always F. Then your map Hn is always F to n, okay? Well, why is nice this property for us? Because if we want to understand the behavior of the random orbit, something that we would like to understand is how it distributes and which properties, for example, in probability, which properties or which statistical properties help us to understand this is the limit laws, central limit theorem, large number law, or logarithmic law, a lot of laws that you can have here that to understand how is the behavior of this orbit, the yellow one, okay, when your maps are random. Okay. And now this is only a motivation for you understand a bigger difference between the random dynamics and the classical dynamics. In general, what we have a measure nu on the diffeomorphism. In that example, nu was the combination of Dirac's, F and G, in the 2 cases. F is the topological support, and we are going to assume that is C2 bounded, okay? In the case that when you have finitely many maps, you for sure have this condition. And what we are going to assume is we assume that there is not a probability measure such that is invariant for all the maps simultaneously, okay? This is our condition. Okay, what is the stationary measure? It's a probability measure that satisfies this inequality. This equality says that it's invariant on average. In fact, if you have an invariant measure, you will have if you have an invariant that satisfies this for every map, you know that this is stationary. But in our case, we don't know. We don't have this measure. The measure that are invariant for all the maps is empty, and then we have only this. For sure, by compactness of the circle and by continuity of the maps, there is at least one stationary measure, okay? And this is a convex set, so we are going to call the extremal points that ergodic stationary measure, okay? Well, in this condition, under this condition, what we are going to see now is some contraction average, but now locally, okay? Local contraction average. For this, we need to have some proximal condition that they are satisfied in a nice local sets. Okay, how I said before, always there is at least one stationary measure, and under this green condition, what we have, Mali said, proof in 17, that there is a finite number of ergodic stationary measure, okay? And I work with him, and well, it's still a preprint, but if you have more, at least 2 ergodic stationary measure, then you have that for every ergodic stationary measure, there exists a family of closed interval, I mean connected set, okay, or arcs, or how you want to call in the circle, and they satisfy these 3 properties. Invariance, it means that for every interval that you have in this family, you go for another whatever map F that you apply, and also it contains another interval, okay? This means this invariance. Also, we have a local proximality. It means that for every connected component, we have proximality. The semigroup is proximal in this set. It means that for every interval that you have here, every 2 points in the same component connect, you can find a sequence that is in the semigroup generated by the topological support of the measure, such that these 2 points can go closer house you want, The union of the components of this family contains exactly one topological support of one of these ergodic stationary measure. Okay? Example. Another example, because the first two examples, they were global proximal. Then they have a unique stationary measure. But here, they are not global proximal. Okay? These two maps, now we are again in the same condition, but now maybe we want to be non-steadily. We put some way for F, some way for G. Okay? What is F? F is a map with 4 fixed points. 2 of them are attracting, 2 of them are repelling. The red one are repelling. Okay? And the second is the same, but maybe a bit rotated, because we want that they don't share fixed point. Because we want that they has this property that they don't have common invariant measure. Okay? Here, the unique invariant measure are the Diracs or convex combination of the Diracs in the fixed point for A, G, or F. Okay? Then this is enough to guarantee that condition. In this example, what we have? We have 2 ergodic stationary measures, μ1 and μ2. Where they live? They live, they are supported between these 2 attracting points for μ1 and these two attracting points for μ2. Why? Because if we are in this arc I1, whatever you apply, you always are coming to, if you apply F, you are coming for this blue, and if you apply G, you are coming for this purple point, okay? And always you came a bit here when you apply F, and then always you are leaving here. What you are doing is this. In fact, this interval, this where is these lines, is invariant for F and G, okay? And what I was saying, that every point here in this I1, they are converging for this interval. That, what is the support of μ1? Well, it depends on the map. They can be, it can be a Cantor set, or it can be all the interval, okay? It depends how they are, if they have this separation condition, or they are okay, they have a overlap. It depends, but they can be a set here. Okay, this analogous is for the second measure, okay? And what we have, this I1 is the family, is a unitary family that we have proximality, okay? Every 2 points in I1, they converge, whatever you apply, F or G, they converge to 0, the distance, and the same for I2. The action of the semigroup in this interval, I2, is proximal, okay? Every 2 points that you take there, always, whatever you apply, well, you can choose your favorite sequence of maps, they are converged. Okay, why I say this? Because we want to understand how is the behavior of the orbit, or at least how they are distributed in the circle. Then something that will help us is the contraction average. Then what we are going to see is contraction average, but for this, I lost this, this. Okay, the contraction average that we are going to see is for these 2 points in this connect component, or for these 2 points in this component component. Okay, so what we have a measure, a probability measure in the diffeomorphism on the circle. We have that there is not an invariant measure for all the maps. Also, we can assume this that the existence of the family, because that, or we have globally comproximality, that is the first case that they studied with Catherine, or you can have, for example, 2 ergodic stationary measure, then you will have this family for every ergodic stationary measure. Then this family satisfies this condition that I said before. The first one is some invariance, okay? The second one is only that the semigroup generated by the support of the measure acts proximally on each connected component of the family. Then what I conclude in the, yes, this is still a preprint, that there exists a metric for this family, for all the circle, but that satisfies, that is contracting average for every component of this family, okay? We have contraction average if you take the 2 points in the same component, in the same connected component for the family. Okay, well, so why I want to introduce this property? Okay, first of all, we have now a big difference between the deterministic dynamics and the random dynamics. And also because this style of property implies nice properties for the operator associated for this system. You can have some contraction in that operator, and you can have some nice properties that what it implies that statistical properties, okay? Statistical properties that I will not say all of them. I will present only the central limit theorem, but you can have almost sure central limit theorem, you can have inequality concentration, you can have another statistical properties also, nice property that say for you how is the behavior of the random orbit, okay? So what we have a process. This Fn, everyone is a random transformation. In this case, it's a random diffeomorphism of class C2. And all of them are ID with the distribution or law nu, okay? And for every x in the circle, we write this sum like this, okay? It means that this is the sum of h along the orbit starting on x. The random orbit according these maps, these random maps, okay? Then what we have, also this is in the preprint, what we have is that is the measure, if the measure mu is a probability that this in fact is the unique ergodic stationary measure supported in this union. Here I am speaking in this condition, sorry, this yellow condition. We have this family that satisfies this invariant and this local proximality, okay? Then what we have that this measure, there is a unique stationary measure, ergodic stationary measure, supported in the union of this interval because proximality and that invariance property. Then for any leeches, you can replace all, of course, leeches here for holder if you want, okay? For every leeches maps, what we have, well, maybe we centralize it. This is not necessary, but okay. You can assume that the integral of h according to this mu is 0. Then this limit exists. It could be 0. In this case, all the orbits are converging for a constant, okay? But okay. In anyway, this exists. This is the important. And then what we have that for any x in this union, you have the central limit theorem. It means that this sum divided by square root of n, it converges in law of the normal distribution with mean 0 variance sigma square. Sigma square is this limit, okay? This when I say this, the convergence in law, it means that if you see the distribution of this sequence, it converges in the weak topology of the distribution of the normal variable, okay? Then what I say was that in this example, if I pick a point here, x, and any invariant, any Leach's function, what I have is the central limit theorem. If I, so according the realization that I will choose Fn, okay? This Fn composed. Well, that is all for today. Thank you very much.